start this session on mining technologies and water resources. I have with me my colleague, I should say, or friend, I should say, Dr. Catherine Truffert, and I am Dr. Pranaya.
Hi, I'm Catherine Truffert, so I'm co-sharing this session. Very glad to be a co-chair as well. So I just remind you for the speakers, you do have only 12 minutes, and 2 minutes before the end, we will just do a sort of team, just to remind you that you have to finish. And then we can try to have some questions just after you talk, but you are really on time. And then question after that also to sum up if some people have to raise some questions.
Pauli, just start. Thank you.
Good afternoon. I'm very glad to be here in India again and have the chance to present this conference our work regarding passive seismic technology for near surface investigation. Our approach is a little bit different from the strict term of near surface. We are mostly dealing with targets that are cannot be considered as shallow, but they are not deep enough to be considered also as deep. So we are talking about targets that can be found below 200, 300, 400 meters down to the first 2 kilometers. And this kind of targets can be subject to be investigated in the sectors of geothermal exploration, deep mining, CBN surveys, and with passive seismic, we're trying to gap bridge the gap between the near surface and deep investigation in an environmentally friendly manner, and also for challenging areas in terms of complexity, geological complexity, and difficult accessibility. So for those who are not familiar with this, what is passive seismic? It's the methodology that utilizes natural recurring seismic signal sources. These can be ambient noise, can be local events, local seismic events, very small events, can be also teleseismic events that occur during the period of acquisition. And these are recorded in standalone sessions that are installed at the surface of the investigated area. And what we get when we are analyzing the information that we acquire. The target is to have 3-dimensional P-wave velocity models, VS models, 3D PVS. Also, we can have information about active faults and fractures that can be also identified by the locations of the events and can be characterized by the focal mechanics. And recently, we had the chance to provide a new technology, which is called the transient source interferometry, body wave interferometry if you want, from earthquake sources we try to generate virtual reflection images like the one that you can see in this example. So the concept beneath this is that with one acquisition scheme we can acquire data for passive seismic methodologies, and this can be separated in earthquake-based, which one the one is local earthquake travel time tomography, reflected wave passive seismic interferometry, and surface wave tomography. And also we have another category that is the noise-based methods, and one that the method that will apply is the ambient noise tomography, or else surface wave interferometry. Each methodology is characterized by the type of the exploited signal. These methods can be used, both of them together, if we have available all kinds of signals, but also we can use only noise methods in case of non-tectonically active areas. So what we record, we usually record in the band of 0.1 up to 30-40 Hz. This is the useful signal for us. And in the lower part of the band, we can have the ambient noise, the surface waves, and the coming from teleseismic events. And on the upper part of the band, we have the local earthquakes and the micro earthquakes that usually can cover the band of about 10 hertz up to 30-40 hertz in terms of micro earthquakes. And this is an example of recording. You can see at the top, signal with noise and any event. We can see frequencies up to about 10 hertz of noise, also very low, 0.2, 0.3. But we can see also here the seismic event, how well it can be separated from noise in terms of frequency content, and of course from each wave. So how do we acquire the data? We are using three-component seismographs that are composed of seismic recorders, 24 or 32 bit digitizers, with some recording sample rate up to 1,000 samples per second, with 3 input channels, and all of them are GPS synchronized and with ultra low power consumption. And shallow borehole, usually shallow borehole seismic sensors, 3-component that can record in the bandwidth of 0.1 up to 100 Hz. Here you can see a typical image of the equipment, the recorder, the sensor, and some example of an installation in one of our stations in a project in India. So how do I acquire the data? Especially for deep targets, and this is the difference between the deep investigations and the shallow ones. We cover large areas with stations spaced at every few kilometers, from 1 to 5 kilometers, and cover areas like in Tripura, we have done projects for ONGC, covered with 348 stations, 4,000 square kilometers. The information that we provided in this case was for very deep exploration for oil and gas, from close to the surface down to 5-6 kilometers was the target that oil and gas industry is interested, but also information useful for structural geologists, down to even close down to Moscow. So, if we would like to have shallow targets, what the acquisition pattern is changing, we need to have very low space stations. So we can see an example from the Netherlands, from Groningen area. We had 417 stations covering only 50 square kilometers, distance, interstation distance of about 350 meters. And you can see also the result, the velocity model, that was a VS93 VS 900. So how do we process our data? Once we have the raw data from the field, we start in parallel doing first the ambient noise tomography work. We are using cross-correlations of time series, of noise time series, and then with dispersion curves of phase and group velocities, we finally come up with a 3D PS model. And this one can be altered, it can be used as standalone in case of the non-presence of earthquakes, or it can be used as initial velocity model for the local earthquakes that we have already analyzed, in order to have a 3D joint velocity hypocenter inversion, in order to generate three-dimensional VP and VPVS models and final, very accurate hypocentral location based on the three-dimensional velocity models. So, just for your information, some results of an earthquake-based method. This project was took place in Greece, in a very mountainous areas, as you can see in the image. The Geological sampling line is lying in the area of the largest bauxite mine in Europe. And the problem that we had to solve is to find out what is happening below, what is happening in this area below the anticline. The production and the flanks of the anticline, there was lots of production of bauxite, but here is an anomaly. And here you can see that the altitude is starting from 1,100 meters and below. So we installed every 500 meters a network of 129 stations, and we have collected in 4 months around 3,000 micro-earthquakes, and from magnitudes of -1.5 up to 3. And we generated three-dimensional VPN PTVS. You have some results here every 500 meters from the surface down to 2 kilometers. In the middle, we have also some two blocks in the last PTVS. And also we run this transient source interferometry for the first time, where we can have virtual reflection imaging for both P and S wave. And here is the result, superimposing the velocity model along with the reflectors that we can identify using this method. You can see that the resolution that can be provided by this method is maybe the highest from all passive seismic methods at this scale. And yeah, thank you. Some also evaluation of these results, superimposition of transient source interferometry seismic section on top of the seismic, and also some evaluation and interpretation along with wells that we have in the area. So also very interesting to say that the velocity model was used in order to reprocess all the vintage conventional seismic data that we had in the area, and the improvement can be seen in this one. At the bottom is with the use of passive seismic velocity model, and it's clear improvement from what they have acquired, the results that can be acquired using the refraction from the seismic. Very quickly, a noise-based method, only noise was used here. Ambient noise from 0.25 up to 1.5 hertz. In the Netherlands, in 1.5 months, 1.5 months, we had the result of three-dimensional VS model in the area. This was for environmental reasons run by Shell. And it's good to mention also finally that we have awarded an innovation, certificate by European Commission because of these passive seismic methods applied in mining industry. Thank you very much.
Good afternoon. We appreciate the presentations. I was wondering, just since you say that it is used for the pre-stacked migrations and comparing to the tomography, could we see any features of the velocity model, okay, in the near surface? I'm talking in the scale of the seismic.
In this particular case, we have to put this very near surface velocity model, let's say for the first 300 meters. From there and below, you can have a very sufficient velocity model that can be used for pre-stacked depth migration. The section can be exactly extracted from the cube along with your line and do your processing if you want further. But for me, the best approach is to use a refraction velocity model for the top layer, combine it with the deeper part with passive seismic velocity.
Thank you, Dr. Nikos. It was a very lucid manner.
However, a lot of other things, and in particular, graphite and graphitite carboniferous sediments are also conducted from polarizable, and in this case, the fourth parameter extracted from the spectral IP behavior or full decay in time domain could be also useful. This is the example for normalized IP phase versus frequency, and you can see that graphite or graphitized bodies chargeability is very low frequency, so we can distinguish it from, say, magnetite, which is very high frequency, and the others which are generally lay somewhere in between. Some examples of how these all could be combined from our experience. This is a mapping field example from a large skarn deposit in Siberia. And the work performed were magnetic field survey and dual frequency. So kind of simplified spectral IP tomographic, electric resistivity profiling, excuse me, because this is mapping, with IP industrialization and measurement. So we have 4 parameters: current resistivity, chargeability, magnetic field anomaly, and simplified spectral IP parameter, incremental chargeability. So if you look at them, we see the decrease of chargeability and increase of magnetic field anomaly, which really means that it kind of magnetite contained in our body. But when we add on top the chargeability, the violet chargeability anomaly, we see that it kind of more complex. It has 2 maxima, so probably these magnetic core, it has outcroppings with different 2 ways, or these are 2 different polarizable objects. And if we look further and add the red line, the simplified spectral IP parameter, we see that these 2 objects are actually different, because the left one is very high frequency polarizable object, which is actually magnetite. The right one is different. So after the drilling and making a map, we see that indeed the left part is the magnetite skarns, the right part belongs to the silicate skarns rich with pyrite and other sulfides. Another example is for sounding. This is a combination of magnetic field survey and 2D audio frequency movement tool rigs. So this is kind of a reconnaissance surveying with the large depth of penetration up to 1 kilometer, and it was used to find some government intrusions, which in this region are potentially cuprum nickel bearing. So the target objects were supposed to be resistive and have magnetic anomalies. And as you see, these 2 methods clearly help to delineate, find, and to find the potential interesting anomalies. So the second part is to try and find optimal modification of your method. And what we mean by optimal, because in the lab it's very simple and cheap to measure whatever you want. So if you have a rock sample, you can do whatever you want with it. But in the field, and especially if you want to reach depths more than 100 meters, you are limited with funds and with work. So you have to always. So there are always a trade-off between expenses and the amount of data you want to get from your work. For instance, like the electrical resistivity tomography method, it could be. It's of course a 3D data acquisition is much better, but it's way too expensive in real life. Almost no one would like to pay for that. So 2D or quasi 3D, meaning like several lines of 2D data acquisition, is way cheaper, but it still can allow you to recover a lot of information. And we usually choose this one. And again, after that, in a 2D tomography, you can use all types of electrode configurations like they use in the many tomography stations. But that's kind of expensive for deep exploration. So for deep exploration, we tend to use some special simplified dipole configurations, which are less susceptible to coupling effects, which have the largest depth of penetration with a fixed length of the transmitter line, etc. Another example is the IP method. It could be made in frequency domain or in time domain. Time domain is generally faster and cheaper, but frequency domain is much more immune to noise. So if you are working for large depths with weak signals, or in the industry with areas with industrial noise, you have to use the frequency domain. And again, the frequency domain can be single frequency, dual frequency, or multi-frequency. Of course, multi-frequency is better, but it's expensive. Single frequency is fast, but there is no spectral information in it. So kind of trade-off, dual or triple frequency, simple thing, like I showed you before, could be a good thing. A couple of examples again. So the mapping example taken in Baltic Shield. This is resistivity profiling with IP, gradient array. I don't remember which are length of transmitter line, but it is a dual frequency modification. So we have not only the apparent chargeability map here, where we can see some sulfide carboniferous schist, but also if you use this additional parameter, which is kind of cheap because only 2 and we see the small ultramassite intrusion here because it has completely different decay rate of the IP. Another example is the sounding, and in this example we use this special dipole array and work in the frequency domain. So we try our best to get the larger signal-to-noise ratio for larger depth of penetration, which results in quite good results. So we have a resistivity and chargeability model with very good quality for the depths up to 500 meters, which is quite difficult to achieve with the regular VRT configurations. And the final thing is about combining various sources and magnetics. And what does it mean? Like galvanic methods with electrodes as a transmitter, and inductive methods with loops or just magnetic, natural magnetic telluric sources. They are basically different in their physics because their sensitivity is different. So the galvanic methods are generally more sensitive to resistive objects, and so they see these resistive objects very good, which is good, but this is a problem because below these resistive objects they see nothing. Because all their attention is focused on the resistors, and if it's a perfect insulator, it just becomes a shield, a screen, and the electric current doesn't go below it. The same thing with the inductive method, they're generally more sensitive to conductors. And if the conductor is kind of very conductive, below this conductor there is a gap without information. So you have to combine them in one way or another to get more information. And also, of course, the different methods, they have different depth of penetration. So you can combine them and make larger volume of the earth power. Like this is a very simple synthetic example of 2D modeling. Synthetic 2D model of highly resistive thick cover with a thin conductor. This is the type of deposits we have in Northeast nuclear region. So if we see the tomography, if we see the tomography only, we see the resistive part very good, but nothing below it. If we use only magnetic tellurics, the situation is inverse. We see the conductive part, but because we don't know anything about the resistors, the inversion tends to make it wrong. But if we include both, the resistivity information comes from here and conductivity from here, and results is much better. And finally, the field example of this is the joint inversion of tomography data. First tomography only, then tellurics only, and then the combined inversion, which allows you to get the depth of 1 kilometer with the detailed and with the resistors placed in the correct place due to the resistivity tomography data. So I guess I don't have time for a conclusion. So thanks very much.
Joseph, MD and CEO, Squadrone Infra Mining Pvt. Please welcome him with a round of applause.
So, good afternoon, ladies and gentlemen. It's a privilege to be here with all the senior scientists, geophysicists, geologists, and these other experts here. Drone-based geophysical surveys using Magaro and drone-based non-planetary mirage. Basically, we are focusing on critical minerals and mineral exploration. That's how we look at what this can be done. I told you, I'm a mining engineer, a first manager, and a DGCA licensed drone pilot. So we are from Squadrone Infra Mining Pvt. Ltd. We are in Bangalore. So we are a group of mining engineers, geologists, geophysicists, GIS and CAD engineers, and drone pilots. So we also fly drones. So we come with the domain, our focus is to have own technology getting into the mining, exploration, and geophysics sector. So our partners, Trios, MSN, Trios from US, AI and ML in mining, MSN from Australia, because we also fly drones underground, inside the tunnels or mapping. So that will not be discussed here. And then drones for geophysical surveys. So we are, it's our partners. So we are the first to fly drone-based hydrometer for mineral prospecting and exploration in India. It was at GMPC's Ambaji project. So this is how we fly. So once we set the flight path along the line of the orientation of the magnetic lines we need, and then you just suspend it on a drone, a magnometer. And then you just fly the drone along these lines. It's all autonomous because you don't have to maneuver. Just set the path, launch it, have your coffee, come back, and you serve it. So this is the magnetometer. So it is called Magaro from Geometrics. It's 1 kilo weight and 1 meter in length. You can take it's got a sampling rate of 1000 hertz, which is 1000 samples per second. And it ranges. The next one. So this is how we do. This is our small video of how we do it. This is not coming here, so I'm taking a bit. Okay, let's go forward with that. So it's a system, therefore, see here you don't need, you can just fly over the trees, no need of approach roads. You can do it in thick forest, marshy areas, Indonesia, with areas we could just fly without entering the areas. It does follow the terrain. They have integrated a system called UGCS. It follows terrain, so it doesn't fly at just one level. It goes as the terrain dips. You can do very low flying, as low as 1 meter. This is Pranaya bushes in Ambaji, where nobody can, geologists cannot work. And this is extension of existing mineral deposits. 1000 samples per second, I already told you. And then you can get all sorts of outputs from there. Let's do this. Slides.
Slides problem you can't fix it. I'm sorry, sir. You can just go forward, no problem.
So what happens is you could run the projects which takes you don't have to enter the areas, and it's got a range of about 7 kilometers. So you can stand in one point and fly your drones, have long lines of up to 7 kilometers. If you can get to the center of the project, run 7 and 7. You can run almost 14, 9 kilometers. And projects I told you, which takes 3 to 4 years, you can do it in 5 to 6 months. And very good for assessment of option blocks. Quickly, let's skip this on this side. This is the power of this technology. This is not to be little any other technology, but this is between a fixed wing and a drone-based. You can see the same area. You can see how the anomalies are. You can see the resolution. Here you're going to fly about 200 meters per second, whereas this you can fly 10 to 40 meters per second. You can do line spacing very close and very precisely. You can do that. You can do slow flying. You can do slow flying. You can do follow the terrain and whatnot. It's used for harsh terrains, forests, farmlands, without exposing humans to danger. Used for nickel, iron, any base metals or critical minerals. To quickly demarcate the areas for acquisition, and I'll come to that. I will discuss that. Exploration of superior depth, but we talk 1 to 1.5 kilometers, what the confidence levels are. Then good for deep seated. And here what happens is you can quickly reach the prospects and projects. So normally what happens is you take time to keep drilling and keep looking for it. Whereas here what happens is you quickly reach the prospects and you know where rejects are, go straight to your targets and start drilling. Use for groundwater, oil and gas, metal detector, and definitely you are not disturbing the environment. And here this is a comparison between a ground-based and a drone-based magnetics. This is about 14 square kilometers. It took 40 to 45 days. And here it took just 4 to 5 days. And you can see the quality of your lines, your data, and what will happen to the what sort of outputs you're going to get. And this is another interesting, you can see how the faults. So we could capture the faults. We just fly and quickly we could capture the fault planes in those areas, in very large areas. And this is another survey for a diamond deposit, the lights. And this was the target, but you could see further deep-seated anomalies, which is going further deeper. And then, so that is with the magnetometer. Magnetics. Now we have come to the next part, which is GPR. We also got the drone-based GPR is attached to a drone. And again, this is much faster in accessible areas, same as that. We got the UGCS here also, it follows the terrain. And then it provides centimeter level accuracy. And say for basically for shallow minerals, the limitation here is it is just about 100 meters. And then it is apart from that, it is used for tailing dams, and subsurface monitoring, pipeline leakages. You can do evaluation of your dams, the stability of your dams, and many more. So this is just an output of from a laterite from nickel deposit, lateritic, and then sapphires, and you could capture where the enriched nickel is in between the border between the laterites and sapphires. So we could map it and get close to it. This is a comparison between traditional how it would have been if it was done with the core drill, and how you get the layering with the GPR. And time-wise, no comparison. So what we do is we fly these drones. First magnetics, like for the nickel, what we did is we first captured the laterites. We follow the laterites, captured the laterites, and then did the GPR to capture further, since it was shallow there in Indonesia. We do that and quickly come to it. And then we integrate. See, when people wanted to go up to 100 meters. Now what happens when your deposits are falling beyond 100 meters? So that's where what we do is we use a ground-based BLF, and we integrate this and we give you the exact target for drilling. So in this process, what happens is you save heavily on your drilling. You have to drill only in your targets, go straight to your targets, make your approach roads, spend your time only on the targets, don't waste your time on others. And you save 60 to 70% of drilling, and you get informed decision making. That's what I was telling about land acquisition. So this is an area of the yellow line is a target, is a tenement, and which they thought that this was the mineralized zone. But after our flying, we told them that this is the non-mineralized zone, and the mineralized zones are going outside, it's overshooting our borders. So we told them better go in. We go and capture those areas. And next is the final part is coming to GPR for gravity and for getting them monitoring and other purposes. We will just show you how we capture leaks in
Today, we present our cutting-edge drone-mounted ground-penetrating radar GPR mechanism designed to detect humidity analysis and cracks in tailing dams with precision and efficiency.
It's a beautiful application. So even when the leaks are below ground, you don't have to even know that you can just fly the drones and then it captures the anomalies, and then you put up the data, and then you go and capture all these leaks, including pipeline, or seepage, or anything. So this is a data application which we are using here at GMDC. So this is it can use for tailing dam selection. This is pre-construction. Post-construction, you can do the gravity analysis, you can do the crack detection, you can do the pipeline leakages. You can do even for large oil pipelines. It is about we are talking to somebody for the 300 kilometer pipeline, where we just fly it and capture all the leaks and the pilferage. That is where in pipelines, oil pipeline, you have people pilferages. So that is something which we can do with this technology. This is some outputs from the GPR. And so finally, this is what we can do. Fast track exploration, cut down your project duration by 80 to 90%. Make new discoveries, greenfield discoveries, which is very important these days. Then information data, accessing inaccessible, and definitely a strong emphasis to ESG. Thank you.
Manager Geology, Central Mine Planning and Design Institute Ltd. Please give him a huge round of applause.
Myself, Sayan Ghosh, Manager Geology from Central Mine Planning and Design Institute Limited, a subsidiary of Coal India Limited. I feel very privileged to present the work which we have carried out in one of the coal fields, which is Mandraga coal field in central India. Actually, it is located in Chhattisgarh state. So prior going to basically the findings of the work, just I'd like to brief out some certain things about coal. You all know that India is having plenty reserve of coal. Around 378 billion ton of coal is deposited in Indian underground carrier, as per the GSI data inventory. Out of which means if you see the power generation capacity of India, around 50% of the power generation capacity in India is through coal. Basically, if you see that the category-wise, if you see the coal deposits, the proved category deposits are only 200 billion tons. The rest are indicated and inferred. What is indicated, inferred, and proved? It depends upon the number of or the density of controlling points which we have, and for designing a geological report or a mine plan, we have to have high confidence of controlling points. Then we can say as a proof category. So the remaining 150 plus 260 means 176 million ton of coal is still to be proved, means brought under proof category. So you can see there are a lot of works still left to prove the coal deposits which are present in the conditions. The Indian coal, definitely geographical location, the Gondwanas cover the maximum coals. Maximum coals which is covered, it is across 8 states as per the current location. The maximum is in state of Odisha and Jharkhand. And if you see the distribution of the coal bearing areas, it is spread across 8 to 9 states of India, including central India, eastern India, as well as southern part of India. Exploration of coal, as far as exploration is concerned, a small video out here. The conventional method of exploration of coal includes drilling of core wells as well as non-core wells. The core wells are definitely we used to drill through our rigs, which CMPDI as well as other organizations like MECL, ITM, and other private partners help us to do for coverage of the data. We acquire the data, we acquire the drill data, we take the core out, we put it into laboratory for few analysis like proximate analysis, through which we can carry out and we determine the grades and all that. I'm not going into very much details about it. So, right now, what the coal industry is doing, they are using seismic to support the drilling data to enhance the momentum of exploration. That's it, because as I told you earlier, that we are still having around 160, 170 billion ton of coal which is yet to be brought under proved category. So we are covering seismic, we are using seismic, we are carrying out seismic, 2D seismic, 3D seismic with our departmental resources and by our private associates which are also carrying out the seismic data acquisition on behalf of CMPDA. This is the regional geology of Son Mahanadi Valley, basically distributed among 7 to 8 states as I told you. But this Son Mahanadi Valley is spread across the central India, covering the states like Chhattisgarh, Madhya Pradesh, Odisha, and some part of Maharashtra. Mandraga coalfield, it is one of the largest coalfield, as I told you, 2,000 square kilometers of area is there. We chose this coalfield as a case study because there are a number of coal seam deposits which are there, which are yet to be converted from indicated category to proved category. So we selected a study area in which the study has been recently carried out in association with a private partner like West Pinnacle Exploration Ltd. Mandraga coalfield, definitely there are a number of coal seams. It is having multi coal seam deposits starting from seam 29 to seam 6. However, all the coal seams which we carry out exploration, which we intersect in our wells, which we interpret through our seismic data, are obviously not commercial, but for that also, for deciding whether it is commercial or whether it is non-commercial, first we have to explore that particular area, and then we can decide upon various parameters. This is a seismic survey which we carried out. This is a just simple layout I am trying to show. We have used 2D seismic here to couple with the drill data. The 2D seismic has been carried out with the help of DMPX, with the help of by our private associate Southwest Pinnacle Exploration Ltd. The typical signatures, as you can see, as I will come to this particular area, that our typical well log when tied with seismic, well to tie, it has been tried to show. Although I am not a very seismic parsing and interpretation expert, but still I will try to explain it to best of my knowledge. You can see there are multiple scenes. Some of the scenes are split. Split means the scenes have been occurring in few areas in top, middle and bottom, and whereas in some areas they have been combined into a particular horizon. So it is very important to separate these splits before estimation of the resource, scene-wise resource. So coal exploration, integrating seismic with drilling, if we see regional exploration, which is usually done by Geological Survey of India through mapping and drilling through wells. Now we use that data, we use that information to particularly interpret and to plan and to execute the detailed survey, in which we use 2D seismic data, we use well logs, and we use core data. And from integrating all these three data, we use to estimate the coal resource as well as the geological structure of that particular area. What is the basic advantage in seismic? As far as coal is concerned, coal is a very low density material. So if it is succeeded and preceded by a high density formation like sandstone or shell, if it is surrounded by that, you will definitely get an impedance contrast. That is basically a very good advantage. But in various cases, there are coal seams which are interbanded. That means within a particular coal seam, with a particular coal horizon, there are multiple bands. So to discriminate those bands, it is a challenging job. This is a study area which we are talking about, Mandragar coalfield, which we selected. This is geographically located in the Chhattisgarh state. Yeah. This I'd like to bring into your kind notice that you can see here, over here. There are a number of seams. Some of them occurs in splits, some of them occurs in splits and combined, some of them occurs in combined state. The thickness of the seams, maximum 16 meters, 17 meters, minimum you can find up to 1 to 2 meters. So it's a very challenging job to discriminate these events in seismic section because of the thickness, obviously because of the thickness. This is the layout which we carried out. We used to carry it out to the seismic. This particular study area was near about 34-35 square kilometers area. And we carried out 10 deep lines. We took 10 deep lines and 10 strike lines across this particular area. The data acquisition, as I told, that was carried out by a partner. So basically, what was the advantage? What was the advantage to use seismic? You can see over in this particular plan that around 60% of this area is covered through forest. So if it is covered, it is under forest cover area, you can use seismic data as a tool. But of course, it is also challenging there because you have to carry a lot of things. But still, as far as drilling is concerned, if you have to convert, if you have to prepare your geological model on the basis of only drilling data, in that case you have to have very high number of drilling points. But in a forest, in a dense forest area, it is obviously challenging. So we use seismic as well as drilling to reduce the quantum of drilling and prepare a model. Definitely the group interval which we selected was 10 meter along 240 channels. There were a few obstacles of which we took offset. Obviously, that remains in every particular area. This is the seismic data processing flowchart in this particular area, and these are conventional methods. I will not go much deeper because, as I told you, that I am not a seismic expert. This is a PSTM and the well time, because we have also carried out well logging in each and every wells which we carried out drilling, and the well time was done. This was the model. You can see that this is a combination of seismic and limited number of drilling data. This was seismic interpretation flow algorithm. But what I told you just, there are a number of seams which occur in plates. Their thickness is low, so it was very challenging task to discriminate those events. Our major task to take out from the seismic sections, to interpret from the seismic sections, was the deposit, the geological behavior, the structure. The structure was delineated through seismic, and as well as far as quality is concerned, means what is the calorific value, what is the ash content, what is the volatile content. These were determined through the control points, although limited, but through the wells. Okay, sir. So this was the final model, which we carried out. Multiple seams you can see. The southern part, obviously, it is very disturbed in this particular area. Northern part doesn't have so many disturbances, but the southern part is having number of faults, which we carried out, which we interpreted, combining these two data. The resource estimation was also done using the seismic section as well as drill core data. And the resource estimation which we carried out through in this particular area using the conventional method. We had the area, we carried out the seismic survey, we had the drilling data, we estimated the area, we know the thickness, we know the specific gravity, 2 wells, so we estimated the resource. Thank you so much.
Now please welcome Mr. Manik Jain, Executive Vice President, Southwest Pinnacle Exploration Ltd. Please give a huge round of applause.
I'm working in an organization called Southwest Pinnacle, and we carry out different explorations of natural resources. So, recently we have carried out the coal exploration in Mandrai coal field, where ERI was also used. So, we have tried to delineate the incrops and the surface faults, position of surface fault through this ERI. So this is about our company, Southwest Pinnacle. So we started in 2006, and we are integrated exploration company, which we carry out every type of exploration from natural resources, starting from metallic deposit, non-metallic deposit, mineral, everything. So if you need anything, any exploration, just remember us. So we have in-house resources. We have a very young management. Today he has received the award also. And these are the resources we have. We have geophysical equipment, we have production rigs, we have drilling rigs, strong technical manpower. Now, about the current study, if you see, the current study is about the coal field which is located in southwestern part of the Mandrai Valley. So this is the area. How do we use the pointer? This one. So this is the area, and this is the block. And so we have carried out 11 strike line and 11 strip line over an area of around 36 square kilometers. Geological data from the 80 boreholes were available. From 80 boreholes were available, and which are also used for interpretation and geological modeling. So in this particular study, we have chosen 8 ERI lines. So they are starting from ERI 1 to ERI 8, and for confirmation of the coal seam incrops in default position. So if you see, look at this. This is basically for the ERI 1, 2, 3, 4, and 5. This is for delineation of the incrops, and the below this one is for the delineation of the fault. So for Incrops delineation ERI1, 2, 3 profile are selected with 50% overlap. I think these are very general things. You can skip this and go further. Sorry, it's gone. So the methodology here we use is we have made 60 electrodes with 10 meter spacing and 590 meter of the spread length. The depth of investigation is near surface up to 100 meters. So data has been acquired using Venner and Venner Schlumberger, and subsequently the data has been processed using REST2D software. Parson actually helped us in doing all this. So concurrently, we have also carried out geological modeling. Something is happening. Doing that. Yeah. So concurrently, we have done the geological modeling and cross sections generated using the Borehole data, and interpreted the Incrops mission that plotted on the geological map. So this is where we have tried to find the Incrops delineation. And if you see here, this part of the profile, you find there is a high resistivity level, and which is basically correlated with our, this is the Incrops, which we have delineated through the geological model. And this is correlating with this. Similarly, here you see the high value distributed, and this it is also correlating. So this is where we have tried to correlate the ERI data with the geological data, and we found that the correlation is quite good. Now here also, if you look at, so here you see there is a high resistivity data. Here also, and this is again correlating with our Incrops missions here. Similarly here, the same Incrops missions, and even the sandstone outcrop has been correlated. This one. Now we have tried to correlate the fault delineation, and here if you see here, there is a fault here which has been delineated through the geological model, and we can find that there is a abrupt change in resistivity between here and here. You see there is a change in resistivity, which indicate this fault is presence of this fault here. Similarly, you can see here. So what we found is that for coal exploration, if you use ERI as a tool for delineation of Incrops and fault positions, near surface fault positions, they are matching actually. So this is another example. So this is, if you see this is the geological cross section which we have drawn using the Borehole data. And the Incrops here, whatever Incrops has been positioned using this here, are matching with our ERI data. If you look at ERI 1, 2, 3, they are perfectly matching here. Similarly, this is the fault delineation. This is the fault. This is the fault in geological cross section, which I showed you in matching with the ERI. So it's very fast. The conclusion is that through this study it has been observed that ERI is an effective tool for delineation of and confirmation of the coal seam Incrops and identification of surface fault. ERI has been widely used for geotechnical and groundwater. I think for coal we should also try to use more frequently. Thank you. So this is our contact information. If you need any of the services, we are there.
Thank you very much, Mr.
I am professor in geology and heading the remote sensing and GS department. Last 23 years, I am working in remote sensing aspect in groundwater, water source, crash square, wetland, and number of the other aspects in natural resource, in crime, in traffic, in master plan. But being a geologist, whatever the work I have done in groundwater aspect point of view, one thing is stuck in my mind 4 or 5 years earlier, that we have analyzed the information, the spectral reflectance of the remote sensing data of the surface. Why not we see the reflectance of the subsurface data? The university has procured the instrument 4 or 5 years earlier, resistivity imaging tomography. Whatever the data, with the help of my student, we have collected from the high altitude and the 4 land basins, the frontal part of Himalaya. This is one of the student presentation, the subsurface investigation of the diverse cover area of the Drumdrum Glacier. No doubt, numbers of the scientists has worked from the last so many years on the Drumdrum Glacier in every part, every corner of India. But this is the first time that we have tried our level best to, from the last 2 or 3 years, to explore the possibility to collect the data of the resistivity imaging tomography of the debris covering the later and the terminal moraines. The student has faced a lot of hurdles, lot of problems, and the presentation which I want to show you is the alluvials, the pelly channels area. That is the delineation of the groundwater in front of part of Himalaya using the resistivity imaging tomography technique. Still, we have tried level best to reach at the part of the 2D, but within 1 or 2 years, we can also find out the possibility of the 3D also. Now, we have, what are the objective is that ultimately to delineate the groundwater potential zone, what are the surface information we have to gather from the resistivity imaging tomography, and we have compared the data with the litholog data. Whatever the data is observed taken by the drilling department or the central groundwater board, we collect the data from them and then we have to compare with that. And ultimately we estimate the yield of the aquifer data from the pumping dust data and structural test data. The pumping dust data, the aquifer performance test data, the step test data will not, from the last so many years we carried out. But ultimately we achieved to compare the data with the resistivity imaging tomography data. That is one of the new things for us. Now, this is the frontal part of Himalaya of the Jammu region. Whatever the 7 or 8 sites we have taken under consideration to carry out the resistivity imaging tomography data with the ERT profile, borehole, litholog data. We find mark the groundwater potential zone, and ultimately we estimate the aquifer characterization and its yield with the help of the pumping dust data, the structural dust data. So this is the map. This is the methods from and one thing I request to the organizer that from the morning to onward, there is no need that I have to explain the method and methodology of that. From the early morning, lot of people have provided us this methodology, number of aspect way. And because of, no doubt, this is today is the interaction of the academia and the universities. But academia ratio is very less, numbers is less. And whosoever has put their abstract and you have given them the opportunity to post a presentation, this is my humble submission and request. Please give them the opportunity because we are the people to use this technology for the academic point of view. No doubt. Okay, so these are the validation and the result of the borehole data of the one side. This is the basically the litholog data, and ultimately we try our level best to compare with the low groundwater potential zone, high groundwater potential zone, and moderate groundwater potential zone. But it doesn't mean that they have to provide us the stairway information. In that side, we have used the Vander and submerger, dipole methods, but here, because of the error, RMS, not supposed to more than 4 to 5%. So that's why we have to not include the part of the banner here. We can only include the part of the submerger and the dipole. In coming time, we also include that part also with the another data when we collect from the frontal part of Himalaya. So this is the dipole 2, the inverted resistivity profile of that area. In the work is the clay and sand, the boulder, sand and boulder. It means majority of the is the aquifer data, and then we have to mark the expected high groundwater protection zone is here. Because of the high resistivity value is also, because the low moderate, we have to assign them the moderate groundwater protection zone. The low resistivity value, we have to mark them the low groundwater potential zone. Because of the color is blue, then yellow, and then red color. So because it doesn't mean that every profile has provided us the same value. There is variation in the submerger according to the depth. They provide us a different color and different value. Now this is the dipole of another side, and we have compared the data with the litholog data, and ultimately we have to mark the 3 groundwater potential zone, low, medium, and high. Whatever the different sites we have taken, and all the sites, the data of the groundwater we have taken from the drilling department. But one thing is that the data which we have collected from the ERT, that data is in a vertical profile. But the data which we collect from the drilling department, the data which you collected that the horizontal profile, the data which you collected from the Department of Drilling, that is a vertical profile. There may be the chances that little bit variation of that data with the ERT data. So that's why we have adjusted according to that data to mark the different groundwater potential zone. So this is the basically the submerger. Ultimately, submerger, Vander and submerger is provide us a good result because the depth is according to dipole is more. And this is here to see the depth of the vertical wave, and it's here. This is all of the good groundwater potential zone marked according to the data. But in that data here, the clay value is more. But the data which we have taken in a vertical profile, there may be the possibility that 100 meters away from that site, there may be the change in lithology of that area. Now, this is the dipole of the 2D inverted profile at the side of the MM college that are adjacent to the university grounds, and this is the 3 side of the MM college ground. According to that, we have collected the data of the 7 or 8 sites. Whatever the work we have done from our own interest point of view. One student has carried out the PhD in the glacier. The one objective is that to resistivity imaging tomography technique. Another student recently have assigned the topic of the from resistivity imaging tomography technique on the frontal part of Himalaya. Now, this is the basically again is that submerger is provide us a good result as compared to the dipole method, because submerger has the depth is more than the dipole resistivity. Now, this is the basically is that the conglomerate and clay, again this is the part of the boulder, wherever the boulder and sand, that the aquifer is good, and it is the high groundwater potential zone is marked on this position. So this is the basically is 7 and 8 known. Because of the last time is again given to less. Okay, no problem for that. I could put with that. Now this is the 7 and 8 side. We have marked the low, high and medium groundwater potential zone, and ultimately we have compared the data with that in discharge and drawdown. Whichever the well is provide us the drawdown, discharge and yield is good, that area it means that having the good aquifer potential zone in that area. So these are the conclusion of that. This is the finding have significant implication of the water source management in the study, and data will be utilized for the future development of planning in coming time. There is no doubt that whatever the cross section we have done, whatever the hydrologic profile have to done, whatever the geological content has given in that, and compared with the actual data. So these are the conclusion of my study. Thank you very much.
Dr. Abbas Singh will...
We have, whatever the information we have created or generated, all the information we have put in our website as a portal, www.jammuuniversity.ac.in. Go to the Jammu University, go to the Department of Remote Sensing, GS, the water source, the cryosphere, the wetland, the other information of all the entire state is available on that site as a geospatial information. Thank you very much.
100 meters, but then to fly higher, that reduces. So we need to fly as low as possible. So we have integrated a system, UGC system which is follow terrain. So that goes as close as. So if you have no trees, nothing there, you just go very close to it. If there's trees, we fly over. Depending on the trees, 15 meters, 12 meters, 10 meters. But to answer your question, it's 100 meters.
I'm sorry. I have a responsibility to correct this answer. Okay. This is a $1 billion question. What's the depth of investigation of GPR? It can be 0 millimeter or 0 to 5,400 meters in Antarctica. So it depends on two factors: the conductivity of the ground and frequency which we are using. So there is no general answer to this question. He is answering it based on his experience in his geological terrain. But this will convey a very wrong message to other audience of the conference. So it can be anything depending on conductivity and frequency. Lower the frequency, deeper the penetration, lesser the conductivity, more the penetration. In seawater it can be 0, in ice it can be thousands of meters. Just adding to your answer.
Thanks for that. You gave the right I'm just telling, as I said, on our system it is black.
In your paper, Mr. Joseph, in your paper you mentioned it can be used for oil and gas exploration.
For magnetics. Used for magnetics, used for oil and gas exploration. Magnetometer.
Thank you, Mr. Joseph. I think it was a wonderful presentation and good awareness to all of us. My just suggestion, and maybe this will be off the platform discussion, where you could have covered the cost of the survey, speed, weight limitations, production rate, what are the software you use, however we can cover this. Thank you. We'll do that. Sure, because of the time I have. Thank you. Can we have questions on ER imaging? There are no questions. If there are no questions, can we go to the geological modeling for questions to Dr. Sayan? So,
We have just carried out the survey in alluvial portions, not moved further. Because when we move toward the height of slope, first is alluvial. So just this survey is carried out along the alluvial, only front part of the alluvial portion, not the upper Shivalik, not the middle Shivalik, not the lower Shivalik.
Mr. Manik, thank you. It was a good integration work.
We have to push more, and there is many things to do, but so we will talk later. And yeah, basically it's my comment. So we have to move forward. So mixing geology and geophysics and probably multi-physics as we do. So today we hear a lot about papers. So combining, so even gravity and seismic and ERT. CSCF, MT, and a lot of techniques. So thank you very much, and do not hesitate to, we have 5 minutes more, so if you do have some questions in the room, I guess, yes, it's the time.
For monitoring drones. I assume if there are strong winds, it might create problems. Is any cloudy environment difficult for such operations?
Drones has got its own limitations. It's one is if you compare it with it's fixed. It is slow, but then it does a very high precision job. And you have got this has to be a suspended drone because the drones and flight should not affect it. So I need some skill to run it. So recently I tested a few weeks back, 2 months back, I tested in Indonesia. And then looking at that, somebody immediately got a flight with them, and they ran for a drone. And they had 2 crashes. So it's a little bit of skill since the suspended drone is different from the normal. But you can learn it. It's not that you can do that. So and then winds, rains. During rains you cannot fly this. Winds is another issue. And basically these are the things which we normally avoid for a drone ride. But in case of, and again, the speed, and you need to go out of the area. You certainly can't turn like other things. You need to listen to players of the game. And then I don't think there is, otherwise it's simply a increase. In case of GPR drone, GPR also is involving, and GPR is interpretation which is involved. So you need to get good interpretation, which is something which is involved. And as Pranaya said, if you have Sayan areas, it doesn't work. You have to consider those aspects. So you have to know the geology. Before you do the GPR, do the drone indicators, know the geology. That's right.
Thank you, Mr. Joseph. Thank you. Pauli.
I would like to request all the authors to please come on the stage for a mental presentation. Dr. Nikos.
Yes, ma'am.
He's there. And I guess Dr. Nikita Zorin is also missing. Dr. Nikita Zorin, are you there?
Yes.
He left, but
His
colleagues.
Please come on the stage.
So I request Dr. Dennis to represent Dr. Nikita. And I would now like to call upon stage Dr. Catherine and Dr. Pranaya Sangvai, our chairperson for this session, to present the mementos for our speakers. Please welcome. Please welcome them to the huge round.
Lady.
Dr. Avtar Singh Jasrotia.
अरे डॉक्टर साहब साथ में हाथ तो लगा दीजिए अच्छी लगते हैं आप
Then we have Mr. Manik Jain. Next is Dr. Sayan Ghosh. And next is Dr. Dennis representing Dr. Nikita Zorin. Now I would like to request Sri S.L. Kapil sir to please come on the stage and facilitate our chairperson for the session.
संगवाई साहब जो है ना मेरे सीनियर हैं 1 साल मुझसे, तो ये उसके बाद ही मुलाकात हो रही है।
ऐसा बोल के इतना बुजुर्ग बना देते हैं कि शर्म आने लगती है।
Turkish shark So let's meet at 9:30. You're welcome to come here by 9 o'clock also. Have to be with us because we will be here by 8:30. That's number one. Number two, all the details of today's proceedings, including photographs,